Hello, this is the fourth lecture in which we are going to discuss the article by Hauser, Chomsky, and Fitch. But first, let's review the previous lecture. In that lecture, we talked about recursive embedding among the relational models, and it was observed that embedding is found in all four of the elementary relational models. That's to say, the nesting of an instance of a model within another instance of a model is found with regard to all of the four atomic models. And the result of this embedding is compound models, and these compound models account for a great deal of the complexity of interpersonal cognition, and by extension the complexity of social life. And this illustrates a concept that was introduced by Abler. It illustrates a particulate system, namely the combination of atomic units, or primes, to form compound objects. Now, particulate, the word particulate, means countable using natural numbers, as opposed, say, to using fractions. And another word for particulate is the word discrete. So, the models are discrete because they're particulate. The number of compound models appears to be unlimited in principle, in other words, potentially infinite, because any imposition of an absolute upper limit on the number of embeddings would be arbitrary. As a consequence, interpersonal cognition appears to exhibit what is known as discrete infinity, as do the natural numbers. Now, given that both the natural numbers and interpersonal cognition exhibit discrete infinity, this raises the question of whether there might be some connection between the human ability to count, on the one hand, and on the other hand, the complexity and variety of our social structures. So, pardon me. Unbounded counting is evidently uniquely human, and the wide range of social variety is also uniquely human. Might there be some connection between the two? That's very close to a theme that's explored in the paper that we're discussing today, the paper by Hauser, Chomsky, and Fitch on the faculty of language. Recursion is not only found in relational models, it's also found in language. And Hauser, Chomsky, and Fitch argue that unbounded counting is an offshoot of language. The recursive system in language is available by accident, making possible a system of counting. It just so happens by accident that recursion in language is available for use in counting. Now, this raises questions about the relation between different mental systems, counting on the one hand and language on the other. Hauser, Chomsky, and Fitch's discussion of the relation between counting and language serves as a model that we can use to ask questions about the relation between language and recursion and interpersonal cognition. So earlier we noted a similarity between counting and interpersonal cognition, namely discrete infinity. Hauser, Chomsky, and Fitch are noting that language also exhibits discrete infinity. So we have three mental capacities which exhibit discrete infinity, and we want to know, is this a coincidence? Is one a side product of the other? Which one is more basic in that case, which is derived, etc.? There is empirical evidence that language plays a role in mathematical cognition. The language plays a crucial role in unbounded counting. Many languages use numbers for precise quantities greater than 4 or 5. And obviously English does, but not every language does. Some languages do not. And this evidently makes a cognitive difference. Consider the Munduruku, There's an Amazonian language called Munduruku, which lacks number words beyond 5. It's been shown experimentally that while native speakers of Munduruku can add approximate numbers beyond 5, they can add approximate quantities that are greater than 5, they cannot do so with precise numbers. I mean, they can distinguish the difference between a big pile and a smaller pile, but they have trouble distinguishing 8 from 9, even visually. A similar case, the Amazonian Pitahan, who evidently lack number words completely. Their language has no number words at all. They are extremely poor at keeping track of precise quantities greater than 3, and this has been shown experimentally. The linguist Daniel Everett, who's fluent in the language of Pitahan, because he lived among the Pitahan for nearly 3 decades, he has suggested that Pitahan cognition and language are both reflections of the Pitahan culture. He proposes that the Pitahan greatly value immediate experience. It's a cultural value. And as a result, they avoid thinking, or any kind of thinking or language that would map onto the natural numbers as a whole. The set of natural numbers is infinite. By reason of being infinite, they stretch beyond immediate experience, and so they are disvalued by that culture. And that's why the Pitahan don't count, or they don't count with precision past 3 or 4. In terms of language, they don't count at all because there are no number words. But in terms of discrimination, they can discriminate up to approximately 4, but not beyond 4 with any precision. And to quote Everett on the Pitahan, grammar and other ways of living are restricted to concrete, immediate experience, where an experience is immediate in Pitahan if it has been seen or recounted as seen by a person alive at the time of telling. And immediacy of experience is reflected in immediacy of information encoding, one event per utterance. So according to Daniel Everett, the reason they don't have number words, and the reason that they're not even able to count with precision past 4, is because of a cultural value. However, this is probably not true. The psychologist Elizabeth Spipin and her colleagues performed psychological studies on home signers in Nicaragua. And what they found was that there's a similar case, similar to the Pitahan, in which culture has been eliminated as a factor. So, these home signers in Nicaragua, they show that unlimited precise counting depends upon number words in one's language, even when one happens to live in a counting culture. Because the home signers in Nicaragua, they do live in a counting culture. They evidently don't share the Pitahan value, if it really is a Pitahan value, to prefer immediate experience over things which lie beyond experience. Now, home signers are people who are profoundly deaf from birth, who create their own sign language because they've not had the opportunity to learn a conventional sign language. Now, Nicaragua, of course, is a numerate culture. Home signers in Nicaragua typically have jobs and they use money, even though they don't have number words. Now, in one of the studies, home signers were asked to describe picture stories in which numbers play a role. Now, usually, home signers are only approximately accurate for quantities beyond 3 or 4, despite living in a culture which encourages precise counting. So to give you an example, there could be a story about 10 sheep standing in a pen, and a home signer might hold out 9 fingers to indicate the number of sheep. Okay. So here's a case in which you cannot point to a cultural value as being the factor. The only apparent factor is the absence of number words in the individual's language. Now, is it merely the presence of numerals that make counting possible? Apparently not. Reciting a list of words will come to an end as a matter of principle, while counting doesn't. In contrast to reciting a list of numerals, the successor function has no upper limit. In other words, for any natural number, there's a greater natural number, no upper limit. The mere presence of a certain set of words, therefore, does not account for the infinity of arithmetic. It can't just be because of one's vocabulary that one is capable of unbounded counting. It must be something else. Now, plausibly, it has something to do with discrete infinity. To be discrete is to be countable with natural numbers, right? So the natural numbers exhibit discreteness by definition, and the natural numbers are also infinite. So the natural numbers exhibit discrete infinity. Language also exhibits discrete infinity. Language produces phrases, including sentences. Sentences are phrases. Language produces phrases, and each phrase is analyzable into constituents, such as words, for example. And the number of constituents in a phrase can be counted using natural numbers. So you have a phrase with 4 words, or maybe with 5 words, but you don't have a phrase containing, say, 4.75 words, or 3 1/4 words, right? Language is also infinite by reason of there being no longest phrase. Just as there's no natural number, there's no longest phrase. For any natural number, there is a greater number, that number plus 1. And likewise, for any phrase, there's a longer phrase. A phrase that, for example, is 1 word longer. So, consider this. The cause is a phrase. It's either a noun phrase or a determiner phrase, but it's a phrase. Well, is that the longest possible phrase? 2 words? No. You can have a phrase with 3 words. For the cause. Is that the longest? Nope. You can also have a 4-word phrase. Die for the cause. And on it goes. To die for the cause. Want to die for the cause. Not want to die for the cause. Do not want to die for the cause. Etc., 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 etc. Until you get to he believes that I said that I do not want to die for the cause. And you don't need to stop there because there's no upper bound. You can keep going. Even he believes that I said that I want to die for the cause can be prefaced with she claimed that. So you get she claimed that he believes that I said that I do not want to die for the cause. And of course, you don't need to stop there either. So you'll notice an interesting similarity here between language and the natural numbers, namely discrete infinity. I mean, that list of phrases that we saw in the preceding slide, that list, it looks like a list of numbers, starting with 2. Right? Now, Chomsky, for a long time, Noam Chomsky, this person, for a long time he's been suggesting that the capacity for unbounded counting is an offshoot of language. And here's a quote from Chomsky. "The most elementary property of the language faculty is the property of discrete infinity. This property is virtually unknown in the biological world." And that's an interesting question, like how rare is discrete infinity biologically? I mean, we can discuss that later. Chomsky claims it's rare. There are plenty of continuous systems, plenty of finite systems, but try to find a system of discrete infinity. The only other one that anybody knows about is the arithmetical capacity, which could well be some offshoot of the language faculty. When you get to questions of the kind we've been discussing here, namely questions of syntax, there seems to be no analog elsewhere in the biological world, down to the level of maybe DNA, or some level where you're talking about biochemistry, really. Okay. Now here is Chomsky's argument, as I understand it. A reconstruction of his argument. He gives two reasons for concluding that unbounded counting is an offshoot of language. Number one, the varying degrees to which mathematical ability is developed in different people, in some cases even remaining unused, as among gatherer-hunters. And, two, minimization of coincidence, given the prima facie improbability of a biological system exhibiting discrete infinity in the first place. Now, one is an argument for counting being derivative, because given the truth of one, counting does not look like a biological adaptation. It doesn't look like a biological, a Darwinian adaptation, right? Like vision, or hearing, or walking, or something like that. If it were an adaptation, you would expect it to be universal. And if it's not universal, you would at least expect it to be universal among gatherer-hunters. In other words, people who live in some approximation of the ancestral environment, the environment for which we are biologically adapted. And yet it is among hunter-gatherers that one very often does not find an exercise of unbounded counting. The Munduruku, for example, or the Pitahan, and there are many others as well, not only those two. So the fact that unbounded counting, this faculty or capacity, is unused, especially in these cases, these like quote-unquote primitive cases, although I don't really like that word, but these pre-agricultural cases. In those cases especially, the absence suggests that counting beyond 4, let's say, is not a biological adaptation. Now that means that it is derivative from something. Now the question is what? What is it derivative from? Well, we want to minimize coincidence, because it's not plausible that the world is full of unexplained coincidences. Discrete infinity is biologically very rare, but you do find it in counting. The natural numbers exhibit discrete infinity, and you do find it in language. So given that counting is not an adaptation, and that language is more plausibly an adaptation because it's universal, everyone has language, it's plausible that unbounded counting is derived somehow from language. Now, Chomsky's argument illustrates the following observation that was made by Bertrand Russell. The form of Chomsky's argument was anticipated by Russell in this quote. According to Russell, the argument in favor of a theory is always the formally invalid argument, in other words, deductively invalid, and yet nonetheless good reasoning, even so. The argument in favor of a theory is always the formally invalid argument. P implies Q, and Q is true, therefore P is true. Now you know that that's not deductively valid, but even so, it is often reasonable to make that inference. Here, P is the theory, and Q is the observed relevant facts. We are most impressed when Q is very improbable a priori. Now, discrete infinity is a priori improbable because it is biologically rare. So discrete infinity itself is a rare thing. You find it in counting, and you find it in language. Given that we want to minimize coincidence, it's plausible that counting is an offshoot of language. That's not a deductive argument, but it is what's called a plausibility argument. In other words, until a better theory comes along, it's reasonable to at least adopt that as a working hypothesis or as the basis for investigation, to probe into the matter, to try to investigate whether that really is true or not. Now, the shared property of discrete infinity casts some light on the sort of calculation or computation that underlies both the construction of a phrase, the construction of a sentence, for example, and unbounded counting. Now, fireflies illustrate this point in a negative sort of way. In principle, a firefly could keep flashing forever, right? I mean, if there were enough energy, enough time, the firefly could just keep going forever, I suppose. Now, is that discrete infinity? The flashing is discrete. You count it using whole numbers, and it could keep on going forever. So is that discrete infinity? It's biological too, isn't it? Fireflies are biological. So is this discrete infinity in biology? Not really. It isn't, because for the human being, there are 2-word phrases, there are 3-word phrases, there are 4-word phrases, and so on. But for fireflies, there's no sort of flashing that corresponds to any number except the number 1. If there's any sense in which the firefly is counting, it's just counting to 1 over and over again. So the firefly's flashing does not exhibit discrete infinity because, well, the number 1 is just a single number. It's not an infinite set of numbers, it's just one number. Now here's the point. The firefly is not grouping the flashes into sets. The flashes are not clustered in any way. Or if the firefly is grouping the flashes into sets, then there's no set with more than one member. Now, in language, by contrast, objects are grouped into sets. And there's no upper limit on, well, there's no upper limit on how complex a sentence can be. The most obvious example of set construction in language is the grouping of words into phrases. A phrase may be more than a set, but at least it's a set. So now we have our first result as to the computations which underlie language. Some of those computations gather objects into sets. The computational core of language must at least include set construction in order for language to exhibit discrete infinity. And the same must be true for counting and also interpersonal cognition. In the last lecture, I discussed this explicitly because I was talking about set construction. I was talking about a binary set-forming operation. That's it right there. You need to gather things into sets in order for there to be discrete infinity. And here's an illustration. Okay. Oh, that's the point I was just making. Now here's the illustration. The next slide should be the illustration. Yeah. The Ishango bone. It's hard to see in this photograph, but there are little notches grouped into clusters up and down the bone on more than one side. All right? Now, the Ishango bone is a relic from the Paleolithic. In the Congo, in Congolese Ishango rather, close to Lake Edward, there was discovered a fossil of a baboon bone, and this dates back roughly 20,000 years. It's known as the Ishango bone. Now, there are 3 columns of marks that run along the sides of the bone, and the marks of each column are arranged into clusters. One column consists of clusters corresponding to the prime numbers between 10 and 20 in ascending order. Another consists of clusters suggesting a numeration system based on 10. And the third column seems to illustrate multiplication by 2. But observe that none of these interpretations would even be possible if the marks were not clustered. The marks have to be grouped together, indicating sets. Whatever person or community produced this artifact was representing natural numbers by recognizing sets. And even if that's not what they were doing, even so, the interpreting these marks as numbers requires us to see them as forming sets. Now, in principle, these marks on the Ishango bone potentially represent all natural numbers, beginning with a finite lexicon, which in this case is just one notch mark. You know, lexicon is a kind of a fancy way of saying vocabulary. It's a little bit more than vocabulary, but roughly speaking, it's vocabulary. Now imagine a vocabulary, a lexicon, with only one item in it, and that item is just a notch. That's all it is, a notch. Okay. Now, by repeating the notch and grouping the repetitions into sets, one can potentially represent infinitely many numbers. Okay. So we know that the discrete infinity of these systems must have something to do with set construction. Okay. It must also involve recursion. Any attempt to explain how discrete infinity can be derived from a finite source must involve recursion. And of course, the source is finite because our brains are finite. The lexicon is finite because our brains are finite. The elementary relational models are finite because there are only 4, and that's a finite number. Okay? The only way you can get infinity out of the finite is through recursion. Specifically, the set-forming procedure must be able to take its own result as input. And this is something we were talking about in the last lecture, which you may recall. Now, the result is that the clustering of objects into sets itself produces objects which can be clustered into higher order sets, superordinate sets. Now, the British mathematician Alan Turing, his recognition of the capacity of recursive instructions to generate an infinite number of outputs from finite input, that recognition was crucial to the invention of the digital computer. Digital meaning discrete, and discrete, well, being a concept closely related to particulate. A digital computer is a kind of particulate system, and it operates recursively. As a consequence, it has potentially infinite output. Quoting Turing, instructions of these types are very important. In other words, the sort of operations we've been talking about that can act upon their own output. Instructions of these types are very important because they make it possible for a sequence of operations to be repeated over and over again until some condition is fulfilled. But in doing so, to obey not fresh instructions on each repetition, but the same ones over and over again. To take a domestic analogy, suppose mother wants Tommy to call at the cobbler's every morning on his way to school to see if her shoes are done. She can ask him afresh each morning. Alternatively, she can stick up a notice once and for all in the hall, which he will see when he leaves for school, and which tells him to call for the shoes. And it looks like the quote got cut off there. Call for the shoes. Ah, yes. And also to destroy the notice when he comes back if he has the shoes with him. So the condition to be fulfilled is that he brings the shoes back home. And when he finally does that, he can destroy the note, and the repetition is terminated. But there's no way of knowing in advance how many times he will have to follow the instructions. The German Romantic poet August Schlegel described language as, quote, an ever-becoming, self-transforming, unending poem of the entire human race. In other words, language is infinitely productive. And yet the contents of the brain are finite. How is that possible? Given that the system can follow not fresh instructions on each repetition, but the same ones over and over again, recursion accounts for the unboundedness which is implied in Schlegel's observation. With a finite lexicon, finite vocabulary, one can recursively generate an infinity of expressions. By contrast, asking Tommy fresh every morning could also conceivably generate an infinite output, but that would be a case of infinite output corresponding to infinite input. Now, beginning with a finite set of numbers, say just the number 1, and a single recursive operation, say +1, all the natural numbers are generated. Using the Ishango numerical system, for any set of notches, there's another set whose members can be placed in a one-to-one relation with that set, plus the addition of precisely one new notch, which is very much like language. For any phrase, there's a phrase of equal length plus n. Therefore, there's no longest phrase. Now, one may wonder, though, if this appeal to recursion might be too strong. After all, given that all natural languages exhibit discrete infinity, why is it that people in some societies are not able to count indefinitely? And the answer is that language is a necessary condition for unbounded counting, but it's not a sufficient condition. Counting crucially depends upon language, even though merely possessing a language does not guarantee the capacity for unbounded counting. Now, the same could be said for literacy. Literacy requires language. You can't be literate without having a language. But that doesn't mean that merely possessing a language will automatically make one literate. Of course not. It's the same with counting. Just because language makes a cognitive capacity possible, that doesn't mean that exercise of the capacity emerges automatically with language. A capacity is not the same as the exercise of a capacity. And there are many illustrations of that in cognition. Here's one. The Acheulean hand axe. About 1.6 million years ago, a regular tool design began to appear, namely the Acheulean hand axe. Now, the paleontologist Ian Tattersall points out that the hominins who first made Acheulean hand axes had existed long before that time. So the species who first invented the hand axe, they were alive long before the invention of the hand axe. Indeed, they had been around since nearly 2 million years ago. So they waited roughly 400,000 years before they invented something that they could have been making all along. Now, Tattersall goes on to point out that a similar delay occurred with regard to Homo heidelbergensis. They first appeared about 600,000 years ago, but they didn't begin to build shelters and keep fires and hearths until roughly 200,000 years later. So merely having the capacity is not the same thing as developing it. Here's a very famous evolutionary biologist, Stephen Jay Gould. Now, Gould observed, and this is relevant to Tattersall's observation, Gould observed that the US dime, because it's so thin, it functions as a screwdriver for certain screws. Now, this is similar to the activation of a dormant potential in biology, insofar as a faculty is put to use long after the period when natural selection first favored it. Now, when something is put to use, when something is put to a use, which is different than the one for which it was designed, Gould refers to this as a Franklin, in reference to Franklin D. Roosevelt, whose profile appears on the dime. So, when you use a dime as a screwdriver, that's a Franklin. Okay? Now, when I say that something is put to a use other than that for which it was designed, design in the case of biology refers to natural selection. I'm not referring to an intelligent designer. I'm referring to natural selection. So, if an organ is put to a use other than that which was naturally selected, that is what Gould would call a Franklin. But you also find Franklins within human culture, outside the realm of natural selection. The use of worn-out rubber tires to make sandals is a Franklin. Given that the tires were not designed to be cut up and made into sandals, this use could go unexploited for a very long time. In fact, it never need have been exploited at all, so long as there were other ways of covering one's feet. Now, the same is true for cognition in some cases. The cognitive capacities of Homo ergaster, these were adaptations for many things, but they were not an adaptation for making hand axes. Ergaster cognition is not a Darwinian adaptation for making hand axes because the ergaster got along just fine for 400,000 years without making any hand axes. On some estimates, Homo ergaster first appeared 2.5 million years ago. And in that case, ergaster existed for nearly 1 million years before making hand axes. Now, be that as it may, it so happens that ergaster cognition, including sensory-motor capacities, and when given some rocks, this cognition brings with it the power to bring an Acheulean hand axe into being. Now, this relates to language. We use language to communicate. Language exhibits discrete infinity, which is biologically very rare, and it's not found in any other known communication system. No other species uses a communication system that exhibits discrete infinity, and that includes non-human primates. There are primate signals, and they exhibit discreteness because they consist of constituents which can be counted using natural numbers. But they don't exhibit infinity. The number of signals for any given primate species is finite, so that's not discrete infinity. What Hauser, Chomsky, and Fitch are suggesting is that language was not originally an adaptation for communication. It was originally an adaptation for something else, most likely cognition. The use of language in communication is a Franklin. It's like taking automobile tires and turning them into shoes, or sandals, whatever, turning them into footwear. It's a use other than the original adaptive use of the organ. Now, that language was initially an adaptation for something other than communication strikes many as very odd. A more mainstream view, at least outside of linguistics, is that language evolved from non-human primate communication systems. But then you have to explain why language is so different from non-human primate communication systems. Another difference involves will, or voluntariness. Language is usually voluntary. I mean, there may be some exceptions. So if you pound a hammer onto your finger by mistake, you might scream a swear word, and you don't have much control over that. But usually you have control over language. You decide what you're going to say. Primate signals, they lack this element of control. The ape or the monkey, according to ethologists, the ape or the monkey it has to emit this signal. It can't hold it in. That's another interesting difference between language and non-human primate signals. Now, according to Hauser, Chomsky, and Fitch, one reason that it has been difficult for people to appreciate that language is not originally an adaptation for communication is because the word language turns out to be very ambiguous. The word language can mean different things. And even when we speak of the faculty of language, that sort of talk is also ambiguous. When we speak of the mental capacity or faculty of language, we could be referring to different things. And so Hauser, Chomsky, and Fitch, they try to disambiguate the word language. And they do this by distinguishing two different senses in which one can speak of a mental faculty of language. They distinguish the faculty of language in the broad sense from the faculty of language in the narrow sense. Now, unfortunately, their use of these terms, broad language faculty and narrow language faculty, is not always consistent. In the article that you read for today, and in a couple of their other articles, and, if I might say so, in their emails, because I've emailed them as well, they do give somewhat different definitions of these two terms. Now, based on what I've read, not only in today's article, but in other articles by these three guys and in their emails and whatever, this is the best that I can come up with for explaining the difference between the narrow faculty of language and the broad faculty of language. You have to be careful to distinguish definitions from hypotheses. So here's my proposal. or my proposal for how best to interpret what they're saying. The faculty of language, in the narrow sense, by definition, is whatever is unique to the mental faculty of language. Or, to simplify it a little bit, the narrow faculty of language is whatever property is unique to language. And there's no guarantee that there is a property that's unique to language. So there may not be a narrow language faculty. If language is unique to humans, as Hauser, Chomsky, and Fitch believe, and as many linguists believe, if language is unique to humans, then the narrow language faculty will also be unique to humans. Okay. Now that's a definition. The following is an hypothesis. The faculty of language, in the narrow sense, by hypothesis, is a recursive procedure, combined with the interaction of that procedure with other mental faculties, which are known as interfaces. So, by hypothesis, you have a recursive procedure, a set constructing procedure, a computational procedure that's unique to language, and hence also unique to human beings. And that computational procedure interacts with other mental systems. I mean, obviously, if it didn't interact with other mental systems, we would have no way of knowing that it's there. And these points of interaction, these points of information flow with other systems, they're known as interfaces. Okay? So, by hypothesis, Hauser, Chomsky, and Fitch are suggesting that the narrow language faculty consists of recursion plus the interfaces, how recursion connects with other mental faculties. Now, there's also the faculty of language in the broad sense, which consists of every cognitive system which can plausibly be included in the mental faculty of language. This includes the narrow faculty of language, if there actually is a narrow faculty of language. Okay? Because, remember, conceivably, there doesn't have to be anything that's unique to language. So, for example, if recursion is not unique to language, if recursion turns out to be a property of general intelligence, then there may not be a narrow language faculty. Now, why would you think that recursion is not unique to language? Well, you find it in interpersonal cognition, and you find it in counting, right? I mean, there's a recursive definition for natural numbers, so maybe it's not unique to language. One thing that needs to be emphasized is that the paper by Hauser, Chomsky, and Fitch is very exploratory. They're developing a research program. It's not a dogmatic paper at all, but very much the opposite. Now, the broad language faculty also includes systems for externalizing language, namely systems of perception and articulation. And in the literature, these are sometimes are known as sensory motor systems, and sometimes are known as articulatory perceptual systems. So speech, signing, speech perception, these all belong to the sensory motor systems, and hence they're part of the broad language faculty. The broad language faculty, now before we get to Gilbert Harman, the broad language faculty also includes conceptual systems of thought, because words and phrases have meaning. Where do they get this meaning? They get this meaning from systems of thought. So that's also part of the broad language faculty. In the literature, these systems are known as either thought systems or they're known as conceptual intentional systems. Now, Hauser, Chomsky, and Fitch, they write that in exploring the problem of language evolution, it is important to distinguish between questions concerning language as a communicative system and questions concerning the computations underlying this system, such as those underlying recursion. Even though we use language for communication, the underlying computational system might be originally an adaptation for something else. It's an important question how the narrow language faculty evolved, if there is one. It's quite plausible that the interface with the sensory motor systems, or that the sensory motor systems are partly an adaptation for language. It's quite plausible that the sensory motor systems are partly an adaptation for communication because they're used to externalize. Right? But that doesn't mean that the recursive procedure itself is an adaptation for communication. And many cognitive scientists believe it to be an adaptation for cognition, such as, for example, Gilbert Harman, who is also a philosopher. This idea that language is an adaptation for cognition is not a new idea. Back in 1987, Harman was saying this, although he may have been influenced by Chomsky, he probably was. Now, Harman notes that there are two uses for symbols. One use is communication, and the other is calculation. Quoting Harman, when you add a column of figures, you're not normally communicating anything, not even to yourself. A similar point holds in reverse. Normally, you communicate the results of your calculation to someone only after you've finished calculating. Right? And Harman continues, the basic use of symbols is taken to be in calculation, not in communication, and where concepts are treated as symbols in a language of thought. Now, this point agrees with experience. People do tend to say that language is obviously an adaptation for communication, or they even equate language with communication. And yet, if you think about your own experience, you're going to realize that a lot of what language does for you is not communication. A lot of what it does for you is cognitive. And even because, for one thing, you think to yourself. Most of the language that you experience is you thinking to yourself. And even when you are using language to communicate, you're usually also using it as a means of thinking. That's one reason why it's so annoying to be interrupted. It's not annoying to be interrupted just because there's a failure of communication. It's annoying because you're trying to develop a thought, and when the person interrupts you, they're not letting you think, right? Now, it is true that there are symbol systems that are used strictly for communication, and they're not used for anything else, like Morse code. But these symbol systems are very different from what is usually called language. They're very different from natural language. So continuing with the quote from Harman, if one cannot think in a language, one has not yet mastered it. That's how closely tied language is with thought. A symbol system used only for communication, like Morse code, is not a language. Of course it is a language in some sense, but it's not a natural language. It's not like French. No. I do think, however, that there's some tension in the claim of Hauser, Chomsky, and Fitch that recursion is unique to language, and their claim that counting is a side product of language. What they mean, evidently, is that recursion evolved as a specific form of cognitive adaptation, which does not include counting. And then just by accident, not natural selection, but by accident, recursion also makes counting possible. Yeah. So counting for them is not an adaptation, but it's an abstraction from an adaptation, right? And also communication, they're suggesting, is an accidental application of the computational core of language. Now, I want to say something about this article. The article by Hauser, Chomsky, and Fitch has a great deal of material in it, and it certainly is not possible to cover the entire article in 1 hour. So, obviously, I couldn't have done that. However, the next 4 articles on the syllabus are very closely related to the article by Hauser, Chomsky, and Fitch. So when we discuss those next 4 articles, we will be discussing ideas in the Hauser, Chomsky, and Fitch article that we haven't covered yet. So we're not done with the article by Hauser, Chomsky, and Fitch. Even so, I would like for you to read another article for next week. I would like for you to read the article Dolphin Social Intelligence by Richard Connor. It's directly relevant to the article by Hauser, Chomsky, and Fitch, and one thing that we didn't talk about too much is evidence that, empirical evidence, controlled experimental evidence that recursion is uniquely human. That issue, Hauser, Chomsky, and Fitch were suggesting when they wrote the article back in 2002 that this question should be opened up to, more empirical investigation. Since then, it's been subjected to a huge amount of empirical investigation involving many species. And the article that you're going to read about dolphins fits into that. There is at least some soft evidence, and I'm emphasizing the word soft. There is some soft evidence for recursive cognition in dolphins, and it happens to be social cognition. There appears to be communal sharing among dolphins. Furthermore, it appears to be complex. It takes an embedded form. So this bears both on the question of relational models in other species, as well as whether or not cognitive recursion actually is unique to humans. So, if you still have trouble getting a grip on everything in the Hauser, Chomsky, and Fitch article, don't worry about that because we're not done with it. But please go on and read Richard Connor. And as I've said before, if you have any questions for me at all, please let me know. Please contact me by email. And I will see you next time. Bye.